All right, hi Chem30 students. This recording is going to help you prepare for our next test coming up, which is going to be on May the 15th, and it's going to cover lessons 12 to 14. Also wanted to mention that I'll probably have to do this in two separate recordings because I think there's probably going to be about 2 hours of material in all, and I just need to take a bit of a break between the two. So again, as always, please practice the questions really hard. All the questions that are on this recording and are on the PDF file, the questions on the test will be quite similar. So let's get started with this then. All right. So we got a picture of someone looking at some chemicals here, just talking about organic chemistry, of course. And I think it's kind of cool that you can start learning to understand some of the structures and the names and that sort of thing with some of the amazing chemicals that are out there. And this is actually the structure of vitamin C. So a lot of everyday molecules that we use in foods and vitamins and that sort of thing, as you get to know organic chemistry, you'll get to know what their structures look like, which I think is kind of cool. So let's go on to the next page then, and it's talking about, was that an ane, or an ine? And of course we're talking about the difference here between alkanes, alkenes, and alkynes. Alkanes, of course, have no double bonds at all. They're just single bonds, and so because of that they're saturated. So when we're thinking about saturated bonds, basically it means that carbons can bond to all four of their possible they're able to bond to four other, atoms or molecules sort of things. So they're able to bond to all four of them when you have a saturated molecule. On the other hand, when you're talking about double bonded molecules or triple bonded ones like alkenes and alkynes, you can see that they're not able to bond to four other molecules. They can only bond to, say, 3 or 2. And so again, only alkanes are saturated, whereas alkenes and alkynes are unsaturated. So again, remember the names for each one of these. All right, so let's think about how do you name cyclic compounds. So cyclic compounds are, of course, compounds where they form a ring, and usually benzene compounds are something different. We'll talk about their names later on. But if they just have a ring, that's a cyclic compound. But how do we come up with their names? Well, remember, we want to know what the different names are for like 3-carbon compounds or 4-carbon, that sort of thing. And if you go on page 546, it'll be a reminder of the different prefixes, like butane is 4-carbon compound, that sort of thing. Pentane is 5-carbon compound. So anyways, once we decide how long the carbon chain is, then we can go from there. So first of all, we'll notice we've got 4 carbons here in the 4 corners. So this is going to be butane. And because it's a cyclic compound, it's automatically a cyclobutane. Okay, so that's kind of the beginning of the name, and we build on that. So we notice we have 2 groups coming off of that. This here is a methyl group, and this is an ethyl group. So which one are we going to put first in the name? Well, what we do is we put them in alphabetical order. And so because E comes before M in the alphabet, we're going to put ethyl first and then methyl. So again, the methyl part that comes second, it gets just tacked on to the cyclobutane. They're all kind of like one word. And the ethyl part is on its own. So it's ethyl methyl cyclobutane. Okay. So moving along to the next question then, what we're going to do now is kind of test our skill at examining the formulas of organic compounds. So we can do 2 things. So we can identify what kind they are, what kind of compound, and what kind of bonds they possess. So let's look at these compounds here, these organic compounds, and let's answer these questions. So first question, which compound is an alkene? So again, we know that alkenes have double bonds. Okay, so we're looking for something that has ene in its name, and we see that the only one there is this one here. So that's the alkene. The next question is, which compound contains triple bonds? We know that alkynes end in yne, and they contain triple bonds, so this compound here is going to be the alkene. All right, so moving on to the next page, question 2C says, which compound is both cyclic and saturated? Okay, we know if it's cyclic, it's going to be a ring compound, and so its name is going to have cyclo something, so cycloheptane is going to be cyclic. And we also know it's saturated because saturated compounds are alkanes, and it's got ane in its name. All right, so a reminder then that this structure here is benzene. It can be represented in two different ways, and so you should know that it's a 6-carbon compound. If you see it this way, you should be able to do it this way as well, to be able to draw it this way. And you want to know that there's only one H coming off of each carbon, because you can see that since alternating carbons have double bonds rather, you can see that the carbons are only able to have one hydrogen coming off of them. So remember that any compound that has benzene rings in it is known as an aromatic compound. Remember though, if it's just a ring compound but is not a benzene ring compound, then it's a cyclic compound. Okay, so the one we saw earlier that had just 4 carbons joined together, that was a cyclic compound, but it was not an aromatic compound. So again, remember, aromatic compounds only have benzene in them. So here's some examples of aromatic compounds. These are kind of everyday compounds you might encounter, and here's toluene, which is the main ingredient in model glue. And this is naphthalene, and it's a pretty powerful compound as far as the smells that you get out of that from mothballs. Okay, so now when we're talking about the difference between aliphatic and aromatic compounds, we already saw that aromatic have benzene rings in them, whereas aliphatic compounds are non-aromatic. So when you're talking about things like the alkanes, alkenes, alkynes, straight chain carbon compounds, those are aliphatic compounds. Okay, so at this point we're going to kind of shift gears. We're going to look at different functional groups. And what are those again? Those are groups of atoms or ions that are tacked onto organic compounds. They're attached to them. Excuse me. And they give those compounds specific properties. Now we see a number of different ones listed in the table here, and a lot of them we're not going to be really looking at that much in depth. But we will be looking at halide compounds, which have the halogens attached to them. So those are atoms or elements that are found in column 17, the second last one in the periodic table. Alcohols have an OH in them. We're not going to talk a lot about aldehydes or ketones, but we will talk about carboxylic acids, which have a double bond to O and also a double bond to OH. They're similar to the esters which follow. Those also have a double bond to O, but instead of being single bonded to OH, they're single bonded to O. We're not going to talk about ethers. Amines we're not going to talk about a lot, but you should know that they are involved in the bonds that are involved in proteins. When proteins are formed from amino acids, amines are the bonds that connect together the amino acids to produce the proteins. Okay, so ester groups are going to be important, as we mentioned. And now we're going to test our ability to recognize the various functional groups that we've just looked at. And so we have a question here where we're going to do that. And please note that in question number 4, I know this looks like a double bond, but it should actually be a triple bond. And so we're going to try to identify these different compounds here. Okay, so we'll start with the alkyne. Well, we know that alkynes have triple bonds. So as we were told that, you know, this one here has a triple bond in it, we know that's going to be the alkyne, right? Alcohols have an OH group, so we're looking for something that has an OH group, and that's going to be this one here. Now, you might think to yourself, okay, this is an alcohol, but it's actually not an alcohol because it has both an OH and it's also bonded, double bonded to an O. and we know that that's a carboxyl group. Okay, so remember, that's not an alcohol. An alcohol is only an alcohol when the OH group is the only special group that's bonded to the C, whereas this one has a double bond to O as well. Okay, so this is our only alcohol. Excuse me. Now, aromatics have benzene groups, as we know, so this one here is going to be the only aromatic group. Again, this is the way we represent benzene. Has a circle in the middle. Now, the last one, unsaturated hydrocarbon. We know unsaturated hydrocarbons have double or triple bonds, so because of that, this here is one because it has a triple bond, and so is number 3. So again, when we're looking at unsaturated hydrocarbons, we're interested in the double or triple bonds that are between carbon. So this is a double bond, so either 3 or 4 can be unsaturated hydrocarbons. All right, moving on to the next question. We're going to pick out a few other functional groups here. So the first one is carboxylic acid, and remember that is like an ester group, but it's double bonded to an O and single bonded to an OH. So that's going to be number 3 here. You can see it's got those two things. And again, remember the difference between carboxylic acid bonds and ester bonds. The next thing we're looking for is unsaturated and aliphatic. That's going to be number 4. Okay, so it's unsaturated because it does have a double or triple bond right here. And it's aliphatic because it's a non-benzene ring compound. Okay, benzenes are aromatic. Aliphatic are straight chain compounds, which this one is here. Okay, so I wrote here only number 4 is unsaturated. So number 3, if we look back at number 3, it is going to be aliphatic, but it's not aliphatic and unsaturated. Okay, so with number 3, it is aliphatic, it's a straight chain compound, but it's not unsaturated because there's no double or triple bonds between the C's. It's saturated. Okay? So that's why we say that only number 4 is both unsaturated and aliphatic. Okay, the last thing we're looking for is a compound that is a halogenated hydrocarbon. Again, remember the halogen compounds are in column 17, and they include things like bromine, chlorine, iodine, and fluorine. And so number 2 has bromines on it, and so it's a halogenated hydrocarbon. All right, so continuing on with naming compounds, identifying compounds. This question 5a says, state which compound is the aliphatic alcohol and which is the aromatic alcohol. So number 2 is going to be the aliphatic or straight chain alcohol. Okay, that one actually looks like a carboxylic acid. Yeah, that one's actually not an aliphatic alcohol. That's a carboxylic acid. Anyways, if it wasn't double bonded to an O, that would be an aliphatic alcohol. And so anyways, let's move on to the next part, which says aromatic alcohol. That's going to be number 1 because it's got an aromatic or benzene group on it, and it's an alcohol. So actually, the one that is an aliphatic alcohol should actually be number 5 because this is aliphatic, right? Because anything other than benzene, benzenes are aromatic, everything else is aliphatic. So this one's aliphatic. Okay, so 5b says, state which compound is the alkene and which is halogenated and unsaturated. So number 3 is going to be the alkene. We know alkenes have double bonds, and so that's going to be the alkene. Number 4 is going to be halogenated because it's got the halogen group, Cl, on it, and it's unsaturated because we know double and triple bonds are unsaturated. So that's unlike number 6. Okay, number 6 is halogenated, but it's saturated. It doesn't have any double or triple bonds. All right, so this question here, it says which groups have ester groups in them? Or rather, which compounds, I should say, have ester groups in them? So remember, ester groups have a carbon single bonded to O and also double bonded to another O. So the only one that fits that bill, or the only ones I should say, are going to be 2 and 3. Okay, so we see carbon double bonded to O and single bonded to O. That's an ester bond, and this one is as well. We've got a single bond to O and a double bond to O. Now, you might think that something like this is, but it's double bonded to O, but it's single bonded not just to O, but to OH. So in that situation, it's a carboxylic acid. It's not considered an ester. It would only be an ester if it was single bonded just to O, but not to OH. Okay, so that's really important to tell the difference there. Okay, so speaking of esters, ester groups are the compounds that give fruits their fruity aroma. So hey, next time you're with someone and they smell pear, you can tell them they're smelling an ester compound. And along those lines, I was thinking, hey, ladies named Esther must be proud to have organic names named after them. Okay, that didn't work. Organic compounds named after them. Sometimes you get a little tongue-tied. Alrighty, so let's go on to the next page here. Hexane and hex-1-ene are both colorless liquids. One method used to differentiate between the two is to add a few drops of orange-colored aqueous bromine to samples of each organic compound. This question here says, state which of the compounds is saturated and which is unsaturated. Okay, so we're looking at hexane and hex-1-ene. Remember that saturated hydrocarbons have all single bonds between the carbons, no double or triple. So we're talking about the alkanes, and they end in ane. So hexane is going to be saturated. On the other hand, hex-1-ene is going to be unsaturated because it's got a double bond, as implied by the ene part of it. All right, so let's talk a little bit more about the difference between organic and inorganic compounds. Organic compounds, of course, are found in either living or once living things, while inorganic compounds are not. So, it's helpful to think about the word chomps. It's not really a word, but it's kind of a word that can help you remember organic compounds. They're made up of these 6 elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. There's some exceptions to these rules. For instance, organic compounds can include, as we know, the halogens, Cl, Br, etc. Okay, so that's kind of an exception. Most of them include just these. Also, although carbon dioxide and carbon monoxide contain carbon and oxygen, which are in this group, they are not considered organic compounds. All right, so which of the following are organic compounds? Okay, well, we're generally looking for ones that contain these compounds. Okay, now this one here is an exception again. It contains one of the halogens as well, and we said that those are included as well. These, you can see, CO and H are among the CHOMPS compounds. This one has C and H, so again, it's among those, and also this one as well. Okay, so we see the ones that aren't included, are ones like this here, which contains iron, which is not in our list. This again, we said CO and CO2 are not organic compounds. Again, sodium is not one of them as well, nor is magnesium. Okay, so we're going to look at 4 different types of organic reactions. There are more than these, but these are some of the 4 most basic types of reactions: addition, elimination, substitution, and esterification. And we'll see that elimination reactions are kind of the opposite of addition. All right, so looking at addition reactions, why are they called addition reactions? Well, atoms are added to a double or triple bond. And these take place when we have compounds that look like this. So again, they have double or triple bonds. So we're breaking the bonds, we're adding the new compound. Then you can see that the elements that are in this compound, the Y and the Z, are now going on to the new compound. And this now is an alkane rather than an alkene. So how would you recognize one? If you're looking at different reactions, how do you recognize an addition reaction? Well, you want to ask yourself, are the carbon atoms in the product bonded to more atoms than are in the carbon atoms in the reactant? Okay, and we can see that they are. These carbons are going to be connected to less atoms than these ones are, because we don't have double bonds now. So that's how we know an addition reaction is taking place. But again, remember, really important, remember addition reactions, they have double or triple bonds. That's what allows us to break the bonds and add these new elements. Okay, so we're adding small molecules like water, or maybe things like the halogens. Okay, elimination reactions, as we said, they're the opposite. So in this situation, we're taking something more complex and breaking it down into the simple compounds that make it up. So it's kind of like a decomposition reaction. Okay, so atoms are removed. These atoms here are being removed from the original reactant molecule, and a double bond is formed. Okay, so again, it's the reverse of the addition reaction. To recognize one, again, you ask yourself, are the carbon atoms in the product bonded to fewer atoms than the carbon atoms in the reactant? And yes, they are. Okay, substitution reactions. In these situations, a hydrogen atom or a functional group is replaced by a different functional group. Now, you recognize these in a different sort of a way. You ask yourself, have 2 compounds reacted to create 2 new compounds? Okay, here we have one compound, and we see the addition sign, another compound, and then we've got 2 new compounds formed. We can see that the Z from this compound takes the place of where the Y was, and the Y takes the place in this compound. So we're switching elements. Okay? It's kind of like a double substitution reaction in general chemistry. Okay. So again, that's a substitution reaction. And the last one we're going to look at is an ester reaction, or you call it an esterification reaction. Now they're always involving a carboxylic acid reacting together with an alcohol. And the product is an ester. And there's also water. We don't worry about that so much. Okay, so carboxylic acid plus alcohol goes to ester. Now, how does that work exactly? Well, we'll see in just a moment. So again, remember what the bonds are going to look like for the carboxylic acid and the bond. Bond for the carboxylic acid, we've got a double bond to O and an OH. But the product with the ester that we're going to have is going to be a double bond to O and an O instead of an OH. Let's kind of summarize the different reactions we've looked at so far. Okay, again, an addition reaction. We're adding small molecules to a double or single bond, and we're getting a single bond. We're adding small molecules to a double or triple bond, and we're getting a single bond as the product. Elimination is the reverse. Again, we're starting with this alkane, and we're breaking it down into a double bonded molecule, or possibly triple, and a small molecule. You can see these are the exact opposite. Substitution, again, it's like a double substitution reaction. We have two compounds that are switching elements between them. And in a esterification reaction, we have a carboxylic acid and an alcohol producing an ester. Okay, so let's look at a question that's going to test our knowledge of that. And actually, I just remembered that I think this would be a good place to stop. We'll kind of catch up on this on the next video because I think we're kind of close to halfway through the material we're going to cover on this video. And so we'll stop at this point and we'll catch up on the next video. All right, so that's it for now. God bless, and we'll get started on the next video in just a sec.